Okay, so good morning. We are going to formally start on this course. So I am first, good morning. So I'm going to first share the screen. So I hope you guys are able to see the screen.
Yes, ma'am.
Okay. Yeah.
Yes, ma'am.
So the topics that we are going to look at today are basically we are going to again start with the basic block diagram of electrical system. Then we will look at the resistance as one of the components in the DC circuit, because we are going to start the course with analysis of DC circuits. As a rule, AC circuits are more complex than DC circuits because the inductance and capacitance, they will also pose a big role. They will play a big role and they will also offer some impedance. So it's going to be a little complex. So we'll go to AC circuit a little later. Then we will look at reduction of resistance, how we are going to reduce the resistance in a ladder kind of network. And ultimately, we will look at probably here itself, I'll introduce even star delta transformation and delta star transformation. I don't know whether you guys have studied this, but we would be looking at this. Okay. And then we would go into KCL and KVL, Kirchhoff's voltage law and current law, and how we can use them for node voltage and mesh current analysis. So this is the way today's lecture is going to progress. Let's first of all look at an electrical system. For example, you think about a torch or a flashlight. It is a very, very simple example of an electrical system where I have a source. The source happens to be the battery. What we have as the battery within the flashlight, that happens to be the source, and the load is the lamp itself. It is going to be the lamp. So these two are connected through a wire in this particular case, or a copper strip, which is the transmission system. Although it is nowhere comparable to the transmission system we talked about yesterday, which is supposed to be at a very, very high voltage. By making use of transformer, we generally step up the voltage. That's what I told yesterday. But this is just a wire and it is going to connect it to the lamp load. This is the lamp load. And of course, there is a small control. The control is in the form of a switch. We can turn it on or we can turn it off. Either way is fine. So this control in this particular case happens to be a switch, nothing better than that. Okay. But nevertheless, this is also an electrical system. This does consume some power, and all these, the working essentially follows all the laws which are followed by any complicated circuit in electrical system. So even to analyze this kind of a small system, we will require basic, some of the laws and some of the theorems which we might have to use for analyzing. So let us first of all start with a simple DC circuit. So in a DC circuit, especially if we are doing steady state analysis, that is, we keep the switch on for a long time, just like a flashlight or the torch. So we are going to probably have a conductor which can be represented by a small resistance, and here is our lamp. So this is the lamp. Okay. So this is the way it is going to work, and we have a switch here. If the switch is kept on for a long time, what we call as the status of this lamp, that is steady state. So the steady state is reached by the lamp once you keep the switch on for a longish duration. Okay. So this, what we represent here, this is the resistance, and all of you definitely would know that when the resistance is a constant, the voltage and current are proportional to each other, which we call as Ohm's law. So this is the basic governing principle in terms of calculating the current in a resistive circuit, especially which is excited by a DC source. So the DC source here happens to be the battery. So whatever is the battery voltage that is going to excite this lamp through a resistance, the resistance is offered by the transmission system, which is the wire here. Fine. Now, as long as the circuit is very, very simple like this, then it is very easy to calculate the current directly. It's not a problem. But if we are going to have series and parallel combinations of resistance, then I'm sure you guys know again. I'm just going to recall this once again. So if I'm going to have, let us say R1, R2, R3 and so on until Rn, right? If they are all connected in series, the current is going to be the same. Whereas the voltage applied, if I am applying a voltage here, which is V, so I'm going to have the same current flowing through all of these. So when I add the voltage drop across R1, R2 and R3 and so on, it is going to make up for the total VDC that I'm applying. So the effective resistance that what we see when we have a series combination is R1 plus R2 until Rn. Right? I'm sure all of you know about this. The same way, when we have a parallel combination of resistances. So let us say I have a voltage source here, and to that I'm going to connect one resistance, the second resistance, the third resistance and so on. When they are all connected in parallel, I'm going to have the same voltage applied through this, and this is going to carry a current of, let us say, I1, and this is R1. This is R2, this current is going to be I2, and this current is I3, and this is R3 and so on. So I'm going to have Rn here, which is going to carry a current of In. So what I get as the total current will be summation of all I, right, from 1 to n. So I can say the net resistance visualized across these two terminals. If I try to look at these two terminals as A and B, I should say 1 by R equivalent equal to 1 by R1 plus 1 by R2 until 1 by Rn. So when I make a parallel combination of resistance, the equivalent resistance will be less than even the least of the resistances I have. Similarly, when I make a series combination of resistance, the effective resistance is going to be greater than even the largest of resistance, right? That is how it is going to be. I'm sure all of you are aware of this. Now, when we make electrical connection at home, what we get is a 230 volts, 50 hertz supply. That is an AC supply. And generally we connect all the equipment in parallel, because if I'm going to have a lamp, it is rated normally for 230 volts. Okay. So if I have to connect, let us say a motor, which is maybe a mixer or grinder, then I have to again connect that motor right across 230 volts. So all of them are generally connected in parallel. If you make the connection in series, it is wrong, because if, let us say, one of them fails, the lamp is not going to last forever. So if I'm going to have the series combination like this is the lamp, and then maybe this is another lamp, and this is going to be a motor. So if one of them fails, all the other equipment are also going to be affected. So definitely series is not the way we generally connect the equipment at home. Only exception what you may see is the decorative lamps, what you use probably during Diwali or any of those things, that they are all generally serial lamps. That's where you see that even if one of them fails, all of them are not going to work together. And in this particular case, each of them, if it is 230 volts, each of them will have only part of the voltage drop. So if you look at 230 volt being applied to two lamps, This is probably going to have 115 volts and this will have 115 volts if I am not going to have the motor connected at all. So obviously the brightness dot what I will get out of this lamp will be much more limited when I connect them in series. Let's try to take an example. Just let us roughly, let me try to demonstrate this with the help of a calculation. So let's try to take 100 watts lamp, which is connected to a 230 volts supply. Okay. So I am showing it somewhat like this. This is my 230 volts, 50 hertz supply. And I'm connecting a 100 watts lamp to this particular terminal of the power supply. So if I am having only 100 watt lamp, I should be able to calculate the current. If I want you to calculate the current that is flowing through this 100 watts lamp, how will you do it? If I want to calculate what is the current flowing through this 100 watt lamp, yeah? How will you calculate the current?
Power equal to VI.
Power equal to VI, exactly. So you are going to say that this is essentially V multiplied by I. So how will you calculate I? That's what I'm asking.
V by V.
100 divided by 230?
Yes, ma'am.
Is that so? Right? So you can calculate this as 100 divided by 230. Another way to do it is, I'm sure you guys know V square by R is wattage, right? So you can say basically this is 230 square divided by 100 will give me R, from which I can calculate again V by R is equal to I. I'm sure all of you know these relationships. Okay. So how much is the current? Can you tell me roughly? Do you have a calculator with you? I think it comes out to be about 0.4. Okay, 0.4. 0.43. Okay, 0.4 ampere. Okay, 0.43 ampere, whatever. So this is going to be the current. Now, if I try to connect one more lamp in parallel, right? Then I'm going to have a current which is flowing here as I, one more current which is flowing here as I. So I'm going to get 2I as the current that is flowing here. Am I right? So in this particular case, when two lamps are connected in parallel, right? In that case, I'm going to have 0.435 multiplied by 2. That is going to be the total current. And if I look at what is the kind of power that is dissipated in each of these lamps, so the total current is going to be 0.435 multiplied by 2. So this is going to be the total ampere. How much is it? 0.87. Okay, so this is going to be 0.87 ampere. Right? Now, if I look at yeah? Yes?
Can you explain the part again when two lamps are connected? I didn't get that.
Yeah, if I'm going to have a 100 watt lamp connected right across the 230 volt supply, how much is the current that is being drawn by the 100 watts lamp? So that is what initially we wanted to check. So if I
when
say,
the second one 100 watt.
Yeah.
You were like two lamps are connected, no ma'am.
Initially we had one lamp connected, we calculated the current, and after that
0.435.
Yeah, 0.435 ampere was the current we got for one lamp. Yeah.
Yeah, till there I understood. I didn't understand why the
When
other part.
When I connect the second lamp across the same power supply. So let us say at home I have two rooms. In one room I have put 100 watts. In another room also now I am adding a 100 watt lamp. Okay. So once I have second 100 watt lamp again across the 230 volt supply, what is the total current that will be drawn from the 230 volt supply at home? That will be basically 2 times the original current of 435 amperes, right? Because This is going to draw a current of I, and this is going to draw another current of I. And if I try to look at the total current supplied by my power supply at home, that is going to be 2 times I, which is 0.87 amperes. So each of the lamp will be in a position to give me 100 watts of power if I am connecting them in parallel. On the other hand, by mistake, let us say I have connected these two lamps in series. So this is my 230 volt supply, and from here I'm going to connect one lamp. This is the second lamp, and both these lamps now are connected in series. Please notice this, right? So I'm going to have, this is originally 100 watt lamp. Will it be able to deliver 100 watts of power? That's what I need to check. So we said that 100 divided by 230 is the current, and resistance is basically 230 square by 100. And
are those in series?
Yeah.
Are those in series, both the bulbs in the
Yes.
lecture explained now? Yeah.
Yeah, these are in series, right?
Okay.
Aren't they in series? You tell me.
Yeah, they are. They are.
Yeah.
Ma'am, one doubt here, both are 100 watt, no, ma'am. If one is 100 watt and one is 80 watt, then also 2I only.
No, it will not be 2I. Obviously, you have to calculate 80 will be the power. So you have to calculate V square divided by 80 as the resistance, right? And that resistance will determine the current, obviously.
Okay.
Right? The
So
wattage of the bulb is determined by what is the resistance.
Ma'am, I have a doubt, but in series, won't the current going through each device be the same?
It will be the same. That is why I am trying to differentiate between the series connection and parallel connection. And why at home we do only parallel connection, not series connection. That's what I'm trying to emphasize. Okay. So this resistance in this particular case happens to be about some 530 ohms or something if you try to calculate. Okay. So this will be 530 ohms and this will be 530 ohms as well, roughly.
Ma'am, after this you explain, ma'am, one small doubt. If, for example, one is 100 watt and the other one is 50 watt, then you have to calculate the resistance separately, then calculate the current for each device and then sum up them, right?
Yeah, when you are connecting them in parallel. But if you are connecting them in series, there is no other option, but the same current is going to go through both.
Yeah, true.
Yeah. So I series in this particular case is going to be 230 divided by 530 ohms plus 530 ohms. So that is about 1060 ohms. Right? So this is going to be the total current. So this current,
That 530 ohms you got using V square by P, right?
V square by P, exactly.
Okay, ma'am.
Yeah. So that's why I had just indicated this 530 ohm here also for the resistance. Okay. So now this is going to be half the original current. So if this was 0.435 amperes earlier, now the current is going to be half of that, which is like 0.22 something, right? So 0.22 approximately, I'm saying, nothing more than that. So if the current is 0.22 ampere, very clearly, I'm not going to get the 100 watts of power from here or 100 watts of power from here. So the power is going to decrease quite a bit to half the value of what originally I was getting, because I'm going to get actually 0.22 square multiplied by the resistance. So this is actually 1/4 of 100 watts. So together I will get only about 50 watts, nothing more than that. From each lamp I will get only 25 watt and together I'll get only 50 watts. So definitely this is not the way we will connect the equipment at home, right? So in general, the series and parallel combination of resistance, it plays a vital role in deciding what kind of connection we want to make in the equipment, especially at home or in an industry. I hope you guys all know about the color coding in the resistance, what we use in the laboratory. the small resistances. Have you studied about that? Color coding in the resistance, that is
Yeah,
you
ma'am.
will have red color and black color
Yes,
rings and
ma'am.
so on. Yeah, so I just want you to recall that this is the normal the saying we remember, B.B. Roy, Great Britain, very good wife. This is what we generally remember for remembering the color coding. So B, for the first B is for black, the next one is for brown, and ROY, red, then orange, and then we are going to have yellow, right? Then green, Great Britain. So the next one is blue, and V stands for violet, and gray, and then white. I'm sure this you must have studied in the 11th or 12th standard. So black stands for 0, brown stands for 1, red stands for 2, orange is 3, yellow is 4, green is 5, blue is 6, violet 7, gray is 8, and white is 9. Right? So normally when you look at the resistance, I'm just drawing a cylinder as a resistance. This is how the resistance will look like in electronics lab, whatever you are going to use. So what you will have is, let us say I have a brown ring. There is no brown here. I don't have the color brown here. So I'm putting red here. So I have one red and one more red. And let us say I have a black. Okay. And I'm going to have basically after this a silver or gold or something like that. Let us say I'm going to have a silver or gold, which is indicative of the tolerance ring. This will be generally thicker. So if it is gold, generally we will say there could be 5% error. If it is silver, there could be 10% error, something like that. So it is essentially telling you how much could be the error that is expected in the resistance. So in this particular case, if I'm going to have, this is corresponding to 2, this is also corresponding to 2, and this is indicative of just before the tolerance ring, whatever is there, it is 10 power that particular ring's color. So if it is black, it is 10 power 0. So this is 22 ohm. Had it been rather than black, if I had had orange color, then it will be 22 multiplied by 10 power 3, which indicates 22K, 22 kilo ohms. Okay, so this is the way you are going to exactly calculate what is the kind of resistance value that you are encountering when you look at a circuit in the electronics lab. Okay, this is important because you are going to perform some experiments eventually once you are in the campus.
Ma'am, excuse me.
Yeah.
Can you explain the calculation part again?
Yeah, ma'am. Yeah. This one okay. Again. Okay. So let me probably take another color that is better. So if I say that this is the resistance that I'm talking about, and these are the two terminals that are available. I don't know whether I'll be able to get this violet or, okay, let me get blue. So blue corresponds to 6. Please remember, blue corresponds to 6. And let us say I'm going to put a green color next. Okay, so this is green. And next, let me say there is a red. Okay. And after that, I'm going to have the tolerance ring. The last one has to be the tolerance ring. Always the tolerance ring will be the rightmost. You have to look at it that way. And then you have to put the digits, keeping this the rightmost. This should be the rightmost.
And tolerance is always gold.
Always it will be gold or silver. Depending upon if it is gold, there will be 5% error that can be tolerated basically. So the manufacturing process will allow 5% error in the resistance. And if it
And there
is
can be any number of resistances, like any number of colors.
generally there will not be more than 3 or 4 rings. Generally you would not see more than 3 or 4 rings. At least I have not seen more than that. Okay. So in this particular case, if we have to calculate this, this blue color corresponds to 6 and green color corresponds to 5 and tolerance ring comes after this red. There is no other ring in between. So whatever is the ring before the tolerance ring, that will indicate multiplied by 10 power how much. So this red is 2 here. So this is going to be 65 multiplied by 100. So this is 6.5 kilo ohm. That's what this indicates. Is this clear? Is this clear? Yes?
We should
Yes,
not
ma'am.
write the tolerance one.
No, tolerance one is just meant for indicating that all the rings have ended now. Nothing else is going to come up. The tolerance ring only tells you how much could be the error in the resistance. How much could be the error? See, it is supposed to be 65K. So it can have plus or minus 10% variation if it is silver ring. It can have plus or minus 5% variation if it is gold ring. You get my point?
Okay.
Ma'am,
Yeah.
so before tolerance ring, whatever is there, that will be 10 power.
Exactly, exactly. So had it been orange instead of, let us say instead of red, if it had been orange ring, then it would have been 10 power 3. You get my
And the
point?
remaining color codes, you have to write as it is, the number.
Exactly, exactly. That's what it is. Okay. So this is the way you are going to calculate the resistance. A couple of more points I would like to indicate in terms of the representation of the resistance. All of you know generally the resistance is represented like this, right? This is how the resistance is represented normally. Sometimes we do represent that as a simple cylinder also. Okay, this is in general indicated for resistance or any impedance, but if it is a DC circuit, it indicates resistance. So this is a simple representation of resistance. But if it is a variable resistance, which we call as rheostat or variable resistance, okay, that is normally indicated like this. Either you just show it like this, which indicates it is a variable resistance, or one more way to indicate is I can have some variation and this is going to be connected and this is going to be connected on the other side. So if I say that this is the variable point what I'm talking about, if it is in point A, for example, it is somewhere in the middle. So I'm going to have only 50% of the value being included in the circuit. On the other hand, if I am going to include this variable point at the end, almost at the end, then the entire value of resistance is included. On the other hand, if I'm going to include this only along point C, which is the beginning of the resistance itself, then I'm going to have literally zero resistance. So I would say if this is the beginning of the resistance, let me call the beginning of the resistance as O. So OC indicates minimum resistance. So on one side, you are going to connect O to the circuit. On the other side, you are going to connect the variable point, which is connected to C. If I say it is OA, this is half the resistance is being included, roughly. And if I'm talking about OB, I'm going to include full resistance in the circuit. Okay, so physically you would be able to adjust the variable point according to your requirement. You may require a high resistance in the circuit for whatever reason. Maybe you want to limit the current. Maybe you want to increase the current now. So you might reduce the resistance from OB to OA. If you want to increase the current further, then you may move it to OC. You get my point? So O is the fixed point that is connected probably to a battery or something. Whereas this variable point is going to be connected, let us say, to a lamp or something like that, like this. So you can increase the current or decrease the current by adjusting the point at which you are connecting the resistance. Is this clear? So rheostat is a variable resistance which comes in very handy in the laboratory for increasing or decreasing the value of current through a circuit. There is one more application of resistance which we call as potential divider. So let us say this is my battery, which is probably having 100 volts. And I want to apply only about 40 volts to a circuit, which is external to this battery. So what I can do is I can again have a variable resistance, which is exactly similar to a rheostat. But only thing is I'm going to take the output from these 2 points. This is the common point for the battery's ground as well as the resistance 1 terminal. The other terminal is a variable terminal. So this is going to be the variable terminal what I have. So depending upon what is the position of this variable terminal, I am going to get a variable voltage here at the output. So I would be able to adjust the voltage that I'm applying to my circuit by adjusting this jockey point. Please remember this is like a 3-terminal device. This terminal and this terminal are fixed terminals which have been connected to the battery. The third terminal what is there, that is going to be varying the amount of voltage which is coming at the output. So this output will be in a position to change as per my requirement by adjusting the variable position, the moving position. Okay. Couple of more points before we conclude about the resistance. Yes?
Ma'am, can you
Explain potential divider again?
Yeah. In the potential divider, basically what you have is a resistance similar to a rheostat, which is connected right across a battery or a DC source. It could be AC source as well. Right now we are discussing with respect to DC source. Let us say this is a 100 ohm resistance, for example. So the current that will be flowing will be 1 ampere, right? If I try to tap the point only from 50% of this resistance, which is 50 ohms, then what I get here will be 50 volts. If the tapping point is at half the distance. If I'm going to make this distance go up by another 25%, so let us say it goes to 75%. In that case, what I'm going to get as the output will be 75 volts. So I would be able to get a variable voltage output, which is obviously less than the input voltage, depending upon the variable terminal's position. So the potential divider is essentially dividing the voltage that is given as the input into smaller fractions so that the output will be in a position to be variable as per my requirement, as per the requirement of the circuit. Is this clear? Okay.
Ma'am, at which end it is 0 and at which end it is full?
See, if I am taking the output between this point, which is the fixed point, how much is the distance from the fixed point? If the distance from the fixed point to the variable point is larger, I'm going to get a larger voltage. If it is very, very close to the fixed point, I'm going to literally get 0 voltage. Get my point? So I'm talking with reference to this particular reference point. If I say this is the reference point for me, with reference to this, how much is the voltage I'm getting? That depends upon how far away this variable terminal is. You get my point?
Ma'am, so
Okay.
reference point is the point where the battery is there.
Where the negative of the battery is there. Not only just battery is there, negative of the battery is there. Because negative terminal of the battery is connected here. Okay?
Ma'am?
Yeah.
So can I summarize what I understood? Yeah, we are using a 100-volt battery. Yeah, and we have connected it to a resistor. Variable resistance with variable resistance.
Yeah.
Yeah, and we have connected that variable resistance to another source, and we are varying the resistance so that the voltage changes.
Exactly.
Okay, ma'am.
Exactly. Only thing is, this is definitely very lossy because I'm going to have 100 ohm resistance carrying 1 ampere of current. So I will have 1 square multiplied by 100 ohm as the loss that is taking place in the rheostat no matter what. This is going to be the loss in the rheostat. I can't help it, but this will be there definitely.
Ma'am,
Yeah.
so if you connect it in the middle,
One of you, please.
Ma'am, here resistance is equal to resistivity into L by A, no ma'am. Proportional to length, no? Resistance. So that's why voltage is also proportional to length.
Exactly, exactly. But please remember, I am also having the wire here. The resistance cannot be connected without some wires. So that is the reason you have to know exactly what is the value of resistance you are connecting. Okay. And then you should also know whether your variable point is somewhere in the middle, somewhere in the 25% zone, 75% zone. You should know very clearly. Got it?
Yes, ma'am. Got it, ma'am.
ma'am,
Yeah.
ma'am, so if you, for example, if you connect it in the middle, it will be 50 volt.
Yeah.
So it is no more 100 volt, it is 50 volt all through the circuit.
It is not all through the circuit, the output. The output is 50 volts. You are still connecting 100 volts. Full 100 volts will be across the resistance, whether you like it or not. Only in the output side, it is going to be 50 volts. Right?
Here losses are spent through heat energy, right?
Yes. Or everywhere in any resistance. Yes.
Yeah. I mean, I was confused. Is it voltage drop or something? Just heat loss through the resistance.
Please remember that voltage is not energy unit. It is only potential unit. When you multiply voltage by the current, it is the power unit. And when you multiply that with time, it is energy unit. Right? So we are actually having different order of explanations for different things. We are telling first of all that 100 ohm is the resistance, 100 volt is the applied voltage, the current is 100 volts divided by 100 ohms, which is 1 ampere. Then we are multiplying that by 100 ohms to say that that is the total drop that is taking place. Then we say I square R or V square by R to say that this is the wattage, the power loss. So there are different things that we are talking about. We are talking about current, we are talking about voltage, we are talking about resistance, then power and energy, all of them. Okay, one by one. Last but not the least, there are two extreme conditions of resistance. Just 1 second. Let me finish this, then we will talk again. Okay. So the two extreme conditions of resistance, I'm sure you must have understood this or you must have heard of this. When you have the resistance almost equal to infinity, we call this as open circuit. So the current under that condition is going to be 0. Whatever be the voltage applied, because you are having open circuit, the current is going to be 0. The other condition which is deadly in any electrical circuit, which is R equal to 0, which is known as short circuit. So in short circuit, literally the current can go to infinity. Even for a very, very small voltage, the current can go to infinity. So these two conditions, especially this second condition, what we talked about is a very, very deadly situation. That is when many of the accidents and other things happen, right? You see fire accident and all happening due to short circuit. And open circuit is a condition where something may not function. In your home, if a motor had been working and suddenly something has gone wrong, maybe it is just that the winding has got cut somewhere. Iron box, maybe it was working originally and now it is not getting heated up. Maybe inside the nichrome coil, something has gotten, dysfunctional, it has got cut. So that is open circuit condition. Yes, Beta, one of you wanted to ask some question.
Ma'am, in the output voltage, the positive and the negative terminals would be same as the 100 watts battery.
Yeah, it will be same as the 100 volts battery because your reference is this, which is plus, and you are applying this with respect to that. So if I have a load, whatever be the load, maybe a DC motor, maybe whatever. So I'm going to apply like this. So obviously I'm going to have plus here and minus here. So this is my load. Got it?
Yes, ma'am. Thank you.
Yeah. So this is essentially, your extreme conditions of resistance, open circuit and short circuit. And we should be aware of this, that, these actually indicate the current to be either 0 or infinity. Fine. So now let us try to take a look at the two laws which are commonly used for calculating the current in any circuit. Okay, so these are known as Kirchhoff's laws. One is Kirchhoff's current law. The other one is Kirchhoff's voltage law. So KVL and KCL. So this is current law and the other one is going to be voltage. So the Kirchhoff's law, the statement is just, it says that at any junction point, the sum of the current is 0. If I try to look at any junction point, the sum of the currents has to be 0. So for example, if I am even talking about a simple circuit, like let us say I have one lamp connected here, another lamp connected here, which is connected to a battery, right? So this is the junction point I am talking about. So if I try to look at, let us say this is the DC source, this is L1, this is L2. I'm going to have a current probably flowing like this, one more current flowing like this, and one more current flowing like this. So if I call this as I2, if I call this as I1, and if I call this as I, right? I should have basically I equal to I1 plus I2. So whatever goes in comes out. That's what it means basically. So if I try to look at this node, I may call this node as N1. This is a junction point which I'm calling as a node. So if I try to add all the currents here, all of them should be adding up to 0. So I can write this as I1 plus I2, which are flowing out of the node, and I, which is flowing into the node, I can write as minus I. So whatever is flowing into the node, I'm showing as minus. Whatever is flowing out of the node, I'm showing as plus. These three things should be equal to 0. So we have to take the direction of the current into account. When we are talking about this Kirchhoff's current law, we definitely need to take the direction of current into account. So if I am looking at any junction point, the current that is flowing into the junction, the sum of the currents that are flowing into the junction should be equal to the sum of the currents that are flowing out of the junction. So this is basically the statement of Kirchhoff's current law. Okay. The second one, which is Kirchhoff's voltage law, KVL, this only states that if I try to sum up all the voltages along a closed path, okay, that is going to be equal to 0. If I try to sum up the voltage along a closed path, or we may call it as a loop, or we may call it as a mesh. Basically what we mean is a closed path. It can be called as a loop, complete loop, or it can be called as a complete mesh. In that, the voltages, the sum of the voltages have to be 0. So for example, if I'm going to talk about a battery here, and there is one resistance, there is a second resistance, maybe there is a third resistance, there is a fourth resistance connected like this. So I'm showing a little complex circuit. So if I try to look at this closed path, I may call this as loop 1. And I may call this as loop 2. Okay. If I may say this is R1, this is R2, this is R3, this is R4. Okay. And I am calling these currents as, let us say, I1, which is flowing through R1. This is I2, which is flowing through R2. This is I3, which is flowing through R3. and this is I4, which is flowing through R4. I should be able to write two loop equations for this according to KVL. So I should say VDC, which is actually a potential increase like this, because this is plus and this is minus.
IC and I4 are common.
They are the same, no doubt. But we can write explicitly the equation this way, that VDC equal to, I can say I1 times R1 plus I2 times R2. Or I can say VDC minus I1 R1, because this is plus and this is minus. Here it is showing a voltage rise, whereas here it is showing a voltage fall. Similarly, this is going to be a voltage fall. So I can write this, instead of writing this as VDC equal to, I can write VDC minus I1 R1 minus I2 R2 equal to 0. This is loop 1's equation, right? And if I try to look at the loop 2 equation, I can write I3 times R3 plus I4 times R4. Yes, of course, I3 and I4 are one and the same, plus I2 times R2 equal to 0. But one thing you have to remember is, if I have taken the I2 direction in this way, then I have to be careful about the sign, because if I try to write it this way, here I'm having plus here and minus here, which means it is a voltage fall. Again, I'm having a plus here and minus here. This is a voltage fall. Whereas if I'm talking about I2 in this direction, it is a voltage rise. I hope you understand. I2 is flowing from plus here to minus here. So the two are definitely different in terms of their voltage fall and voltage rise directions. So I have to write I3 R3 plus I4 R4 minus I2 R2 equal to 0. So this is the equation for loop 2. So I'm going to have essentially 0 voltage. Ultimately, if I sum up all the voltages that are across each of the element in a loop. Okay, so this is KVL, and the KCL tells me that the sum of the currents in a node or a junction point is 0. So these two are extensively used for really solving a lot of circuit problems. So let us try to take a look at, for example, let's look at resistance reduction, and let us look at KVL, KCL, both. Okay. So let me take some numerical example, one of them, and then let us try to solve it probably using resistance reduction as well as something else. So I'm going to ask you guys to simply help me reduce this problem. Okay, let me take 100 volt source. I have just taken arbitrarily some value, and I'm going to include some resistances like this. Okay, so this is the resistance network I have included. Okay, so let us say this is some 10 ohm, and I'm going to have another 10 ohm here, and I'm going to have 20 ohms here. Okay, now I'm going to have, along with that, again another 10 ohm, and I'm going to have 20 ohms here. And finally, I'm going to have again 10 ohm here. I'm sure you can immediately tell that this is 10 plus 10, 20. 20 and 20, when I connect in parallel, I will have 10 ohms. This 10 and 10 put together will become 20. And 20 and 20 here, I'm going to get 10. And that 10 will add up to this 10 ohm. So I'm going to have, this is equivalent to having 100 volts and 20 ohm. And I'm going to get this as the overall circuit. Fine. Is this clear? So I'm going to have 5 ampere of current flowing through this. Yeah. So this is going to be 5 ampere of current that is flowing through the circuit. So what I'm going to have is 5 ampere here. Now I have to apply current division. You guys know how to apply the current division rule. So let me say this is some R1 and this is some R2. So I'm going to have the current through R2 will be equal to R1 divided by R1 plus R2 multiplied by whatever is the I total. Right? That is how it is going to be divided. So I'm going to have this to be I total is 5 multiplied by, I can say this is 10 divided by 10 plus 20, which is 30. So this is going to be 5 by 3 ampere. So if I'm going to have 5 by 3 ampere flowing here, how much will be here? 5 minus 5 by 3. So that is 10 by 3, right? You are going to have 10 by 3 ampere flowing here. Now again, we have to check how much will be flowing here and how much will be flowing here. Please note this is also 20 ohms. This is also 20 ohms. So the current will divide equally. So I'm going to have 10 by 6 ampere here, which is actually 5 by 3. So again, I'm going to have 5 by 3 ampere here. So we have solved the circuit, right? So this is one way of solving the circuit. Another way of solving the circuit in this particular case, I can use, for example, KCL or I can use KVL. Either way is fine. Yes, yes, beta. Somebody wanted to ask something?
No, we can again use Kirchhoff law.
Yeah. So we can use Kirchhoff's law. So let me first of all redraw the circuit probably to make it, is it possible to make it with 2 loops? We can do that. So otherwise we can hold on to the 3 loops itself. Okay, so the last loop I am going to draw with single 20 ohm resistance because 10 plus 10 is 20. So I'm going to write it as 20. This is also 20. This is going to be 10 ohm. This is going to be 20 ohm.
20s will be in parallel, right?
Yeah, these two 20s are in parallel. So then I can show it as 10 ohm.
Again with the 10.
Yes, exactly.
Yes.
So I am just showing it like this. Now if I have to draw the KCL loop equations, I can write this as I1, for example. This in general, I'm going to show as I2, and this in general, I'm going to show as I3. Please note, this 20 ohm resistance is going to have 2 currents flowing through this. I1 is in this direction and I2 is in this direction. You get my point? Similarly, if I try to look at this 20 ohm resistance, this is also going to have I2 in this direction, whereas I3 is going to be in this direction. So when I write the equation for example, loop number 1, if I may call this I1 current flowing in loop number 1, so loop 1 equation is going to be 100 volts is equal to 10 times I1 plus 20 times I2, I1 minus I2. That is loop 1 equation. Loop 2 equation will be, there is no voltage source connected. So 0 volts is going to be equal to, I'm going to have 10 times I2, right? Plus 20 times I2 minus I3 plus the last one, another 20 times I2 minus I1, depending upon what direction you are using as positive, what direction you are using as negative. I'm sure the third equation you can write correspondingly 0 volts is going to be 20 times I3. So this is 20 times I3 plus 20 times I3 minus I2. So these are the three equations now, and I have three unknowns which are I1, I2 and I3 which we can solve. Okay, so we'll continue with this in the next class. We'll write this equation.
One small doubt.
Yeah. Yeah.
Mom, in the above one blue with blue color which you drew,
Yeah.
the circuit.
Yeah.
So you divided 5 ampere using the formula R2 is equal to R1 by R1 plus R2 into I total, right?
Yeah.
So you got 5 by 3 near 20 ohm.
Yeah.
So other 20 ohm is there, no ma'am? There also 5 by 3 because these both are parallel.
Yeah, and both of them are 20 ampere.
So
20 ohm. Both of them are 20 ohm resistances, so it will divide itself into two halves.
Yes, ma'am.
Exactly
then
two halves.
5 by 3, no ma'am, because 10 by 3, matlab it should be 5 by 3, no ma'am, not 10 by 6, right?
Yeah, it is 10 by 6 is same as 5 by 3.
Okay, sorry.
Yeah, right?
Yes.
Yeah. So what we will do in the next classes, we'll start from the same KVL problem and continue with this